morning, and I would like to present you our project related to the development of a fiber optic biosensor that could be used in the detection of some cancer biomarker. And this is a project that we have been running together with the School of Medicine of our university, as well as the Institute of Physics at the CNRS in Nice in France. So the idea is to use optical fiber biosensors, and in general, optical fiber biosensors are devices fabricated on the tip or along an optical fiber. There's a quite particular class of sensors because they are quite particular in terms of technology, a little bit alternative to the electrochemical sensors that are, of course, the majority of the biosensing technologies of nowadays. But in general, they have been used to detect biomarkers, they've been used to detect bacteria, viruses, and hormones with a quite successful rate of works. The idea, if to use fiber optic biosensor for our kind of works, is to have a label-free technology in which the selective detection of biomarkers or biomolecules is achieved by functionalizing the surface of the fiber at a specific sensing point with the bioreceptors that we would like to have. And we can study the performance of those elsewhere and then have a platform that is actually ready for biosensing. So there are several methods for functionalizing. Some of them use fiber serialization or APDS, APDMS. Some of them use metallic thin films, plasmonic sensors do that. Some of them do sort of hybrid methods in which we have, for example, the combination of APDS layers and additional metallic layers or even nanoparticles to have more different patterns and specific type of events that we can actually detect usually with an increased sensitivity. The idea of using optical fibers is that they are quite easy in terms of fabrication, although this usually seems to be one of the problems because the scalability of some of the manufacturing is a bit problematic nowadays. They can operate in situ, they can operate in vivo. The fibers is so small and so thin that if you make a reflective probe, actually you can place basically within a medical device and operate directly in vivo in real time, and with a very good biocompatibility ensured by the fact that the fibers are made of glass. So as a matter of fact, it's one of the most inert materials that we can have. The idea is that if we use a label-free approach, we can split the biological part and study it separately from the actual sensing device. And that's nearly the approach that we would like to do. So in our work, we want to start one step behind and try to control the propagation properties of the optical fiber and see that these is one of the building blocks of our system. So one of the propagation problems that we would like to achieve is the scattering that occurs within the waveguides. And normally, the fibers that you have on the market, they are engineered to reduce the scattering to a minimum, as this is a loss factor for our technologies. Now, what we are trying to do is do exactly the opposite. We want to maximize the scattering. And what we did, particularly with our research partner based in France, in Nice, is to try to have defects fabricated directly in the preform of the fiber, and then draw the preform at different temperatures and different speed in order to see how these devices, these defects basically translate into the fiber. And what we have basically is that depending on the size of the devices, depending on the defects that we are able to implement, and notice that these are done in the preform. So as a matter of fact, these are basically just dopant materials for the fiber. We don't have particles yet at this stage. But when drawing the fiber, you can have all sorts of defects in the fiber. And choosing, for example, high temperature and average speeds, you can have the fiber doped with nanoparticles. But if you, for example, reduce now the temperature, the defects tend to cluster much more and form elongated particles up to the point where you have only elongated particles. And these events tend to increase by a significant amount the scattering. We are talking about a 10,000 times increment in terms of scattering. These are some of the fiber at the preform level, and these are some of the SAM of the fiber. How can we make a biosensor with this? In general, the fiber itself does not have a sensitivity to the environment. So you can use that for physical sensing, but not for biosensing. So one option that you have is to remove the cladding of the fiber, exposing it to the outside. And this is something that we have done. Another thing is to taper the fiber and have nearly the similar effect. What you see right now is that this sensor and this sensor do require an actual fabrication. That means you have to have a fiber and you have to etch it, or you have to taper it. Tapering is quite fast. Etching can be done rapidly and reliably, particularly using methods derived directly from the electronics, which uses etching much more than we do in optics. But still, there is a fabrication. What I would like to show is how we can avoid even the fabrication and just do that with the normal splicing and cleaving that is done typically in telecommunication. That's exactly the work that we call a semi-distributed interferometer. So the way we have done that is basically to take our semi-distributed interferometer that actually, I inverted the slide, it's better to start from this point, that is done in this way. So that's a standard single mode fiber, telecom fiber like the one that you have for any long haul telecommunication system. That is the cheapest fiber that you have, and that's manufactured in the order of tens of millions of kilometers per year. So if you want to build a cavity out of this fiber, how do you do? One way you can do is to cleave the fiber at the tip and create a mirror. And that mirror is placed directly in the contact with the surrounding environment. You have a sensitive layer here, but that's not a cavity because it's only one mirror. You know that you need at least 2 mirrors. What happens if you place now one of the fibers right here that has a very high scattering and you make this length quite short? So this fiber does have enough reflectivity, even though we're talking only about scattering events, to create a cavity. It's a weak cavity. You need a good hardware to interrogate it, but it's enough to make an actual sensor. The only problem is that you have all sorts of reflective bands right here because we're talking about a fiber that has a high scattering centers. So depending on the fiber that you're using, you might have sensors that have spectra looking like an interferometer, or sensors that have spectra looking almost like a random interferometer, or sensors that have gigantic holes in the reflection spectrum, and all sorts of patterns that you have right here. So that's exactly how you did it. Notice that the fabrication now is extremely easy because you just basically take the fiber, splice a scattering fiber, and cleave it. And that's it. That operation takes about 10 seconds for a skilled operator. And in fact, by the time we submitted a paper to nowadays, we have fabricated something around 500 sensors. So that's actually something that nearly every researcher in the lab can do. So the way it works in terms of biosensing is that we need a hardware with a quite high precision because standard interrogators do not see such low level of reflection. But interrogators that come from the field of distributed sensing do. And while there's a quite expensive piece of hardware, we're talking about an instrument that has a resolution of about 1 picometer and 0.02 dB. So the precision that we have exploiting telecom fibers is high. That's more or less the structure of the fiber, a simple splice. The chart is not on scale because a good operator can keep this cleave short to a few hundredths of micron, or even in some cases even less. And basically we functionalize the whole fiber. Of course, the only thing that matters is the functionalization that we have right here. For this project, we have studied CCL5, Chemokine ligand 5, which is a biomarker that in conjunction with our School of Medicine, we have been studying as a prognostic factor for some type of cancer. So the idea is to functionalize the surface with the anti-CCL5 antibodies that we have studied in a different matter using Western blotting, and for which we have already proven specificity and reliability in terms of detection. And functionalizing then the fiber surface using a simple serialization process. And this is how it works with some of the experimental sensors that we have achieved. So that's one sensor that has achieved a sort of average sensitivity using fibers that have quite a large amount of extended nanoparticles. This is the interferometric spectrum. It looks like an interferometer, like a bad one, like an interferometer modulated by some random function. That's exactly how it looks like. But if you look at each one of the peaks or valleys, we have also a quite good sensitivity. Due to the filtering process here, you don't see, but there is also tiny wavelength shifts that if you exploit the good functionalization can be enhanced. So as a matter of fact, you can even track the intensity or a wavelength shift. We haven't done that yet, but that will be our next step. And the sensitivity rates we achieve here are in the order of 240, 400 dB per refractive index unit, depending on whether you want to interrogate each one of the peaks. They all have a different sensitivity. But as you can see, the sensitivity rating that we achieve, at least if you select the right sensing point, it can be quite high. And we have studied nearly all the possible fiber combination that we can have, achieving the top sensitivity that is in the order of 700 dB per refractive index unit, but values around 300, 400, 500 dB per refractive index unit, kind of norm if you select the right sensing point and the right fiber. clearly, having a large randomization of the scattering centers, the spectra are random, so you cannot really control them beforehand. But a simple calibration will allow you to find the sensitivity, and it's quite simple process. So when the fiber has been functionalized, we detected the CCL5, and as typical for fiber optic sensor, the output that we obtain is a function that responds usually in a log linear way. So we have basically an incremental output for exponential changes of concentration. That's a common point of label-free fiber optic biosensor, particularly those based on single mode fibers. And we have been able to detect spectral changes for concentration ranging from few attomolars up to few nanomolars, and using a pattern that basically is more or less in this way. If you zoom into each one of the peaks, or you will find basically a similar pattern within the optical spectrum. And we have been measuring that into PDS. We have been doing serum measurements, and the pattern actually is kind of similar. The limit of detection is very low, but that's again a common point, particularly for this type of measurements that are done in a static way. These are actually the data that we have sampled using, if I'm not mistaken, one sensor. One sensor for each measurement, but we have a similar chart actually done studying the repeatability as well. The limit of detection in general are quite low, so the technology is able to respond to even tiny changes of the protein concentration. That is because in general, even if the change is quite tiny, the resolution of our hardware is extremely good, and we don't even need to do a lot of averaging in order to achieve that type of results. We studied separately the specificity using another sensor and comparing the differential outputs when we change its concentration with respect to other proteins, and the data seems to confirm that actually the antibody seems to work quite well. So as a matter of fact, the system can be specific. And I just want to point out that such a sensor that responds to large concentration changes is a good tool for investigative studies where you don't yet have a precise concentration range that you want to detect within the biomarker that you want to investigate. So as the study is done for CCL5, we hope to be able to port this platform into much more type of biomarkers. So in conclusion, what we presented is a rapid and sensitive methods for achieving refractive index sensing and biosensing based on optical fiber. And to the best of my knowledge, that's the simplest one in terms of fabrication that we have so far, and yet having a spectrum that you can demodulate and obtain either an intensity change or a wave shifting pattern that we can achieve. And it's actually extremely fast. So you really take few seconds to make a sensor, and with a normal splicer, you don't need expensive fabrication facilities. So as a matter of fact, it seems to be a quite promising technology. So the biofunctionalization method, of course, is what makes a sensor specific. So I hope that this is something that we can, for example, multiplex to detect multiple biomarkers, exploiting some of the methods that I discussed already in my tutorial on last Sunday. And of course, we have a low detection limit and a wide range of response as typical for most of these technologies. So, thank you. That's the end of my talk.